Section P.1, P for preview, is real numbers and their properties. And we're going to start in talking about the real number system. One way to do that is to look at it in a sort of diagram view. So this looks like one big box split in, it's 2/3, 1/3, just because the other side needs to have lots of boxes inside of it, okay? So there's 3 boxes embedded inside of the box on the left. All of the numbers that we're going to talk about in college algebra are considered real numbers. And what we're going to do is we're going to divide them into 2 different categories. The real numbers are either rational, that's the left-hand box over here, or they are irrational, and that is the right-hand side. And we're going to start with irrational. An irrational number that you have encountered before, an example of one, would be something like square root of 2. So what does it mean for it to be irrational? Well, it kind of means it's not rational. It's exciting, right? So irrational means it cannot be written as a fraction or a terminating decimal or a repeating decimal. Another irrational number that you for sure have seen before is pi, right? It never repeats, it never stops when you look at its decimal expansion. Another example, and this one you may or may not have seen before, is the number e. If you haven't seen it before, it's not a big deal. These are some examples. Obviously, there's lots more we could write into this box, but we're just giving a few examples. Now, on the rational number side, what we're actually going to do is we're going to start with the little box in the middle, and we're going to work our way outward. The little box in the middle are called natural numbers. And they're sometimes also affectionately called counting numbers. These are the numbers that you first learned to count with when you were a child. And when you first learn to count as a child, you start with the number 1. So that's what natural numbers do. So these are our natural numbers. But then there's that kid, and that kid that says, but what happens if I take 3 and I subtract 3? I need a number 0, and that's not a natural number. So we need a new category, and this new category is called the whole numbers. Now, whole numbers include the counting numbers from before, but they also include the number 0. So they're not very different from natural numbers, but they do have an extra digit. And then there's that smart aleck on the bus that says, okay, smarty pants, then what happens if you do 3 minus 5? And you're like, well, I don't have a number for that. That's not possible, right? So we need negatives. And if we expand our universe to include those, we have created the integers. So integers are, one way of thinking about it, the positive and negative whole numbers. So they include everything we've already done before, and they're additive inverses, right? The numbers that when you add them to themselves, you get back 0. And then our last category, where we're going to put a few numbers in, some example numbers, is the rational category, rational that aren't integers so far. So it's going to include, all the numbers I've written so far are considered rational numbers because they can be written as a fraction, right? I can take any of those numbers I just wrote on the board and write them over 1, and I have a fraction. Not a very exciting fraction, but it's a fraction, right? Okay. So there are numbers that also can be written as fractions that can't be reduced like this, right? So those numbers would include things like 5/2. Yeah? It's a fraction. You could include decimals, because you can change a decimal back into a fraction. So if you had something like 1.7, that's a rational number. You can even include repeating decimals, like 1.3 repeating. That's a rational number. Okay? So the decimals themselves are not what makes something rational or irrational. It's how the decimals expand, yes? If they repeat or if they stop, then they're considered rational. If they don't repeat and don't stop, they're irrational. Now, we're taking this real number system, all of these real numbers, and we're going to put on them operations. Operations like addition and subtraction, multiplication and division. But in order to do that, there are some properties that those operations must follow. And in order to take a look at that, we're going to look at some examples and talk about what property is being presented by the example. So in the first one, you see -3 times the quantity in parentheses x minus 4. And I'm going to show you the property that looks like this, where we take the number 3 and we move it through the parentheses. And we multiply -3 times x to give us -3x. And we multiply -3 times -4 to give us +12. And what is that property called? The distributive property or distribution. Okay, so that's one of our properties. You take multiplication and you can distribute it through addition or subtraction. Our second property we're going to look at is a property of multiplication and a property of addition. So this one is the example of multiplication. It tells us that y times x is the same as x times y. And you know that to be true. 5 times 2 is 2 times 5. It's also true for addition, right? 5 plus 2 is the same as 2 plus 5. However, it doesn't work for subtraction. 5 minus 2 is not 2 minus 5. And it doesn't work for division. 5 divided by 2 is not 2 divided by 5. So it only works for multiplication and for addition. Does anybody remember what this property is called? It's a good example because we're using multiplication, but it works for multiplication and addition, so it has a different name.
Inverse.
Not inverse. That is another property, but not this one. This one's called commutative. Oh, you're like, oh yeah, I remember that word. And if you don't, that's okay. But it's called the commutative property. Good guesses, everybody. All right, our third property that we're looking at says that when I have three numerals, like I've got the 5, the 4, and the variable y, and they're all multiplied, and I've got some parentheses sort of attached in there, right? But it's all multiplication, agreed? There's no addition in the middle of it or subtraction or something like that. It's all multiplication. That I could change the order or the grouping of the multiplication like this. I could regroup the 5 and the 4 together first and do that before I did the deal with whatever y is. And that property is called the associative property. It's changing the groupings and how they're associated, right? It's associative property. Now, let's actually just do problems 4 and 5, and then we'll talk about the property that's being presented there. What is the absolute value of -3 over 4? 3 over 4. And what's the absolute value of 3 over 4? 3 over 4. And this is the property of absolute values, right? The property presents itself, and your book calls it this. It tells us that additive inverses have equal absolute values. So this phrase inverses, I think Amos was the one who said that word before, additive inverses. These numbers, -3/4 and 3/4, are considered additive inverses because if you add them together, you get back to the identity 0. Okay? That's what makes them additive inverses. So we're saying any number and its opposite, if you take their absolute value, you get the same thing. And the reason for that is because absolute values really are just measuring distances back to 0, like on a number line. It's always measuring a distance back to 0. And distances are positive quantities, right? When I talk about how far it takes me to drive in the morning, I say it's 20 miles for me to drive from home to here, and it's also 20 miles for me to drive from here back to home, right? So we always talk about it in a positive sense. And absolute values have that flavor to them as well. Now, thinking about that, and with these absolute values, we're going to move exactly into distance. The distance between 2 points, A and B, on a number line is an absolute value of B minus A. Now, the cool thing is it really doesn't matter whether I wrote B minus A or A minus B, because we're going to take the absolute value when we're done. So to show you that that works, we're going to do an example to show you really that it doesn't matter which order we do it in. We have two numbers that are given, -3 and -14. We're going to try to find the distance between those two numbers. So depending on which one we call A and which one we call B, might depend on whether we set it up as -3 minus -14. Maybe you did that. Or -14 minus -3. So let's take a look at this and see what we get in each direction. Now, in both cases on this particular one, we have minus a negative, right? What happens when we subtract a negative? What is that? It's addition. So in both cases, we can take the quantity and we can change it from -3 minus -14 to -3 plus 14. Or on the other one, from -14 minus -3 to -14 plus 3. So if you were doing this problem, you're not going to do both of what I'm writing down. Okay, you're just going to do one of them. I just want you to see that it really doesn't make any difference which one you do. On the first one, what is -3 plus 14? That's 11. And what's the absolute value of 11? It's 11. On the second one, -14 plus 3, what's that? It's a -11. And what's -11's absolute value? 11. So the order didn't make any difference. Because of the absolute value, actually, right? Yeah, because of the absolute value. All right. Okay, the next thing we're going to take a look at is exponents. When we have a positive integer n, and we have the expression a raised to the power n, right, like 3 raised to the power 7, it means we are going to repeatedly multiply something by itself. So in this case, it's the a that's repeatedly multiplied, and how many times would it be multiplied? N. Somebody said it, yeah. N times. Whatever that exponent is. Whatever the exponent is tells you how many times you multiply it by itself. So on our first example, -3 to the 4th, how many times am I going to multiply -3 by itself? 4 times. So it'd be -3 times -3 times -3 times -3. That's what it would be. And if you were to take -3 times -3, what would you get? 9. And we do it twice because there's 4 of them there, right? So I've got 9 times 9, which gives me 81. On the second one, what do you suppose is the difference? I mean, it's not in the parentheses, so how will that affect what's happening? Good. So the negative is going to stay. The negative is not affected by that exponent, right? It's sort of in front of what's going on. And what we really have is 3 times 3 times 3 times 3, the 4 times, and it's the 3 that's written 4 times, and the negative is written at the beginning. It's not part of what's being raised to the power 4. And we already established that when we multiply 3 together 4 times, we get 81. So this ends up being negative 81 instead of positive. Those parentheses matter, right? They make a difference. All right, our last order of business for today is order of operations. Order of operations is really important. We're going to do several examples. But before we do the examples, you probably remember an acronym that looks a lot like this. Please excuse my dear Aunt Sally. So I'm going to sort of mess with your mind just a little bit to tell you that we likewise could have written PEMDSA or PEDMSA. We can move some of these letters around, and I know nobody probably ever told you that. Maybe they did. But the kicker is really that these two and these two are grouped together, and their order doesn't matter. Parentheses matters to be first. Exponents matters to be second. But once you get to the multiplication division, those don't matter. In fact, once you get here, you should be moving from left to right on these. So P, as we said, is parentheses. And E, we just spoke about a minute ago, was exponents. The M and the D are to multiply or divide, again, from left to right. And the A and the S are to add and subtract, again, from left to right. So let's do an example over here. Where will I start on problem number 9? The parentheses. And P for parentheses means simplifying inside of parentheses, right? Not removing them. It just means cleaning up the inside. So if I simplify the 2 times 3, what do I get? I get 6, and I don't need the parentheses anymore. Now, while there are no parentheses here, there sort of kind of are. The 4 minus 6 is inside of a notation that tells us that it has to be acted upon independently of the rest of it, right? It's a grouping symbol as well. It's just sort of got this extra layer of absolute value-ness to it. So what is 4 minus 6? It's negative 2. But then the absolute value of negative 2 is 2. So this ends up being 5 minus 2, which is 3. Let's try another one. This inside of this parenthesis has addition, subtraction, and multiplication division going on. It's got more than just one operation. So will I start with the 5 minus 2, or will I start with the 2 times 8? 2 times 8, because it's multiplication. So we will do 2 times 8, which is 16. And then, still inside those parentheses, what is 5 minus 16? What is it? Negative 11. Now, when I'm taking a look at this, I've got negative 3 times negative 11, which is, yes, and you didn't say it, but you meant it, positive, right? There's no negative anymore because it's a negative times a negative. Oops. And then our last thing is to take negative 2 plus 33, which gives us 31. And it's positive because the 33 is the larger of those two quantities. All right, number 11 has parentheses, but there's nothing to simplify inside of them. I can't combine the 4 and the negative 2x, and I can't combine the x and the 5. So what will I need to do instead? Distribute. That's back to those properties from the first slide that we looked at, or second slide that we looked at. So what's 5 times 4? 20. 5 times negative 2x? Negative 10x. Negative 2 times x? Negative 2x. And negative 2 times negative 5? Plus 10. Really common mistake is to forget the negatives there and write another negative down. So be careful with those negatives. Our last thing then is to combine the terms that are alike. So I've got a 20 at the beginning. Is there another term that is like 20? The 10. And 20 plus 10 would be 30. And then these last two terms here are actually alike as well. I have negative 10x and negative 2x, which gives me negative 12x. Okay, we have one last example, and it's a really quick one. Okay, so bear with me while we finish that up, and then we'll be done for today. This is kind of like an application of what we're doing with our order of operations. We have an expression, a squared minus bc over a, and they give us values to plug in the place of a, b, and c. So the a value is -2. So where we have an a, we're going to put -2. And we're going to put parentheses to indicate, remember, the parentheses matter. It's all of the -2 that's a, so it's all of the -2 that's squared. Minus the b value, which was -3. And the c value, which is 0, over a, which is -2. Now this is a pretty simple one. You can probably do many of the steps all at once, but just to be clear, let me make sure that we're doing them in the right order, just in case they would get more complicated later, which they will. Exponents should be first because there's single digits inside parentheses, so the exponent here is the -2 squared. What is -2 squared? It's 4. Minus -3 times 0 over -2. Now, it doesn't look like there's any parentheses to be simplified inside of, but the entire numerator needs to be simplified before I can act upon it by the denominator. So looking at the entire numerator then, I have multiplication involved. The multiplication has a -3 times 0, which is 0. That's very friendly. Love zeros. They're great. So I have 4 minus 0 over -2. Again, you can move more quickly as you're working on your own later, but just to be sure we're all clear, we would completely simplify the numerator to give me a 4 first over the -2. And then what is 4 divided by -2? It is -2. Yes.